So welcome everybody here in Geneva in the watch party. Welcome to Zurich and welcome to any other person who is connected somewhere. My name is Jens Wigen. I am a librarian at CERN. I have today the honor to introduce the speaker, Thea Aarrestad, who actually is my favorite speaker these days, you know. Thea is, as myself, Norwegian, so you can say that I might be biased. And for some time, I thought I'm probably just biased. But earlier this year, I got confirmed that I am not at all biased, because all of a sudden I read on the internet that Thea had received the Early Career Scientist Prize from the International Union of Pure and Applied Physics, you know, which then confirmed that I'm not biased. It was absolutely correct. If you look at the title of this talk today, Smashing Particles and Crunching Data, how CERN uses artificial intelligence to explore the frontiers of physics, you might think that this is a very irrelevant talk for librarians, but I can tell you it is not. I have heard the versions, I think, of these presentation before, and I can assure you that this is very relevant for librarians and very inspirational. For those of you who are connected with Zoom and you would like to rest incognito, I suggest that you switch off your camera and that your questions will be submitted through chat, because this meeting is being recorded and it will be put online afterwards. So with that, I would welcome you to the floor, to the stage. Please, Thea.
Tusen hjertelig takk, Jens. And thank you all very much for having me here. I'm really excited to get to talk to a room full of librarians about my favorite topic, which will be a little bit of history of particle physics together with the history of computing and AI and what we are really using AI for today. And I think myself, as well as many people in this room, I wake up every day and I think we're in a crazy time of kind of hyper productivity that we never had before. You know, when I used to do my homework, I used our 80-volume lexicon. I sat on the floor and I looked for different tree types. And last week, I took my 9-year-old daughter to the climbing gym, and she took my phone and she used the Google AI companion to figure out whether trees sleep or not. So now she can kind of look up these facts in an instance of a second, and it would take me ages previously. And whereas the last time we saw this revolution with the PC was due to silicon transistors, this time is due to basically massive data and massive compute. And I think Ilya said it very well, the founder of OpenAI, who's made ChatGPT, that today has really been made possible due to two very simple things: big data and big compute. So extraordinarily large neural networks that are large because we have the compute to fit them and train them, that we can train on very, very large data sets. And this is today. And at CERN, we've actually been dealing with extremely large data sets and big compute for a very, very long time. And so here on this plot, you can see different data set sizes. So here you have Netflix streaming. Here the size is roughly proportional to the size of the data set. Here you have what's uploaded to Facebook, Instagram content, and the amount of data that we produce at the LHC is up here, 40,000 exabytes of data per year. And a colleague from Google asked me, well, you guys used to have really big data, but I guess that's not really true anymore with the internet and everything. But this size is actually a sixth of the whole estimated size of the internet every single year. So you have to deal with massive amounts of data, and we have to process that data because what we can afford to store is just very, very little. So the history of compute and CERN goes hand in hand. So we actually have a very long history of beginning with compute early on. So our very first computer was actually just hiring Wim Klein. So he was our very first computer. He calculated the 73rd root of a 500-digit number in 2 minutes and 43 seconds. So we utilized this man in order to do all our massive computations. And at some point, the field of fundamental physics was reaching a limit where we couldn't go further because the calculations we had to perform were impossible. And in this kind of crazy, lucky coincidence that often happens in science, digital computers became available. So just as we were hitting a roadblock, computers arrived. And we were one of the very first purchasers of computers. In 1958, we bought this huge thing, Ferranti Mercury, which was not transistor-based at all. It had vacuum tubes, magnetic core storage, all these boxes here. And these huge boxes filling a whole room would not even fit the single LHC collision today. Now, why was having these computers so important to us? Well, before we had accelerators and the detectors we have today, we had what's called spark chambers and bubble chambers, and they would make pictures kind of like this. So this is a proton scattering in a spark chamber is wires, and when a particle goes through, it creates sparks. Or bubble chambers, where this hypersaturated gas, and when a particle goes through, it creates little bubbles along the track. And so we used to have scanning ladies that would work from 7 a.m. to 10 p.m. and scan these pictures manually. They could only do 4-hour shifts. The record is to analyze 1,000 such pictures, 750 pictures in 4 hours. Very slow. During the night from 10 p.m. to 7 a.m., men did that job. So in a typical experiment, you maybe took 100,000 photographs at a rate of 10,000 per day, and the analysis took weeks and weeks and weeks. So what actually happened was that we bought these computers and we designed CERN IEPs, instruments for the evaluation of photographs, to go from 35 millimeter photographs to something that is digitized on a computer where you can fit a track. And yeah, these CERN IEPs, I think it's very funny because today we talk about replacing physicists with AI. They actually said, they had a joke, which was that this actually stood for the elimination of physicists. So that was kind of the standing joke at CERN at the end of the 50s. So we've already been in this AI problematic phase before, and it turned out to be completely okay. We're still around today and we do great physics. So in 1963, we finally got our first transistor technology computer with tape storage, and finally a compiler and a programming language. So you maybe know Fortran. That only arrived with this computer right here. And now we could really analyze like hundreds and thousands, 100, 200, 300,000 images of spark chamber data with these. I also put this in because I just think it's incredibly cool. In 1972, CERN had the most powerful computing system in Europe. And this is that computer landing at the Geneva airport on a Pan Am flight from the US. And here they're kind of rolling it over the tarmac. So it's massive. And now you saw the size of the room before. Now this whole computer is in this massive hall. Here you can kind of see the main frame. So now we were really entering big compute. And we went from analyzing photographs to taking data digitally out of the sensors themselves and straight into the computer. So bye-bye photographs at this time. Where are we now? Well, the CERN data center has now, we have one new site that just opened, 450,000 processor cores, 10,000 servers. We handle 45 petabytes per week, storage capacity of 3 exabytes, so massive, and a huge reading rate. But that's not all. That's the compute we have locally at Tier 0, our computing site. We also have a worldwide grid consisting of 170 sites around the globe, 42 countries, with 1.4 million computer cores. So really massive, massive compute. In order to share all that information of the data we've collected, you've probably heard about the World Wide Web coming from CERN, Tim Berners-Lee. This is the very first website that ever existed, documenting basically www and HTTP protocol. And what was really cool with this coming from CERN was that we instantly released it into the public domain. So it was open license, everyone could use it. And 10 years after it was released, there was this conversation that was overheard at their annual workshop. Well, next year, one delegate was overheard to say, while tucking into a spring roll and sipping Chardonnay at the evening reception, courtesy of Bill Gates, Microsoft will have bought the World Wide Web. So it's fantastic that things we're developing in science goes back to the community itself. Now, we also have a very close development with AI. So we just celebrated our 70th anniversary. This is a picture from the first shovel that was dug at the CERN Mera site at the Norwegian National Day, 17th of May in 1954. And just 4 years before we thought we need a big lab for physics in Europe, Turing had published this seminal paper on computing machinery and intelligence, where he proposed the Turing test, where he said, if a machine could carry on a conversation over a teleprinter, so here you can also think you're typing something into ChatGPT, that was indistinguishable from a conversation with a human being, it's reasonable to say that that machine is in fact thinking. So people are starting to think about studying the building blocks of matter with CERN at the same time as people are asking questions about the building blocks of intelligence and whether or not we can reproduce it. So when we started building CERN, we didn't yet have a formal agreement establishing CERN. That only happened a few months later. September 29th, 1954, 12 states, including Switzerland, Norway, France, Germany, signed this convention that established CERN as an entity. Exactly 1 year after, McCarthy, a professor at Dartmouth, coined the term artificial intelligence, saying, could we have such a thing as machines that think? And he organized a summer research project on the topic of artificial intelligence, together with a list of other scientists. And these people aren't just random people, I looked them up. And McCarthy himself created a Lisp programming language, which was very much used for a very long time. Minsky himself co-advised 2001: A Space Odyssey, and there's actually a character in that movie named after Minsky. This man went on to be the chief architect of the first mass-produced scientific computer and wrote the very first assembler we had. And Shannon is the father of Boolean algebra and information theory, and you probably know his name very well. In 1957, CERN built its very first accelerator, our synchrocyclotron, 600 MeV, to do basically nuclear physics and particle physics. And we had it for 33 years until 1990. And at the same time as the synchrocyclotron, the perceptron appeared in machine learning 1 year after. And the perceptron is basically the building block of all the neural networks we have today, where Frank Rosenblatt here speculated that these type of network could eventually maybe be able to learn, make decisions, and translate languages, which they are today actually doing. The problem for Rosenblatt was that he went to school with Minsky, who did the artificial intelligence summer school that we looked at 3 years ago. And he said, this will never work. This is such a stupid idea. And that started what's called the AI winter. So for 50 years or so, people kind of abandoned machine learning and AI because Minsky said it was a bad idea, plus other reasons. Then something crazy happened in 2012. At CERN, we discovered this tiny particle that the whole standard model of particle physics relies on, and the theory breaks down without the existence of this particle. In September 30th, 2012, it was demonstrated that AI could outperform classical algorithms and humans on computer vision tasks. So in 2012, there was an image recognition challenge where there was a submission called AlexNet from Alex Krzyzewski, Ilya Sutskever, founder of OpenAI, and Jeffrey Hinton, who got the Nobel Prize in physics, so big names in AI, who really said, hey, AI can do crazy things. So they proved that Rosenblatt's perceptron was actually a very good idea. It was built on that. Where are we today? Well, now in 2025, at the LHC, we're really measuring the tiny parameters of the standard model of physics to look for any sort of deviations that can hint at new physics. So we're testing it to extreme limits by doing very precise measurements. At the same time in AI, they're taking this perceptron building block and saying, hey, maybe this is not the right building block. Can we shape the building blocks and come up with completely new types of neural networks? So we kind of have this nice co-development throughout time. In this day, we talk a lot about AI for accelerated discovery. So I think this example is one of the nicest ones, AlphaFold, where before AlphaFold, we only knew how 17% of the proteins in our bodies fold, which is crucial to how they function. After AlphaFold, a neural network could predict how proteins fold. We now know over 98% of how the proteins in our body behave. So this has really paved the way for novel drug discovery, treatments, etc. And what I didn't mention is that in the discovery of the Higgs boson, we heavily relied on machine learning in order to be able to detect it as early as we did. So we actually used a combination of 5 different machine learning techniques to be able to announce the discovery of the Higgs. If we hadn't used machine learning, we would only have discovered it 5 years later. So here you can see for a lot of Higgs discovery channels, so different final states where we look for the Higgs, the additional data that would be required without machine learning. So it's really helped us accelerate how fast we can do discovery. Now, we have over 40,000 papers on using AI in particle physics so far. From the very first of them, which is a very strange paper by Mlodinov and Stamatescu from the Max Planck Institute on how you can use machine learning to steer a turtle. Very, very strange. And actually, this guy, I'm a bit of a fan of him. He wrote for Star Trek, for MacGyver, the best show that was ever made, and co-authors The Grand Design with Stephen Hawking. So already then they started thinking about AI, what can we use it for, and what are we using it for very, very crucially today. For that, we have to go back here. We have this massive amount of data, big, big data. We've had big, big compute for a very long time. And we can only, if we have to filter that data extremely fast to go down to a smaller number because we cannot store all of it. How fast do we need to filter it? Well, if you look at the time needed to process the data versus how much data is going through the system, again, you have Netflix, 4K streaming down here, you have the Google Cloud here. We are all the way down at very, very low latencies and very, very high throughputs. And we need to run our programs on specialized hardware like FPGAs and ASICs, and not on commercial hardware like CPUs and GPUs. So where is all that data coming from? And why do we have to be so fast when we process it? So here's the LHC that I suspect many of you know, 27-kilometer long ring, 100 meters underground, and we have 4 so-called collision sites, CMS, LHCb, Atlas, and ALICE. We inject protons into this ring. So everything starts out with a little tank of hydrogen, roughly this big, enough to feed the LHC for forever. We push them into this first separator. It has electric fields, and the job of this separator is to take the electrons away from the protons, so we have a pure beam of protons. So we keep the electrons back, and we inject the protons into the ring. And the size of this beam of protons is roughly 2 millimeters, so very tiny. We inject those protons into the ring in a bunched way. So at any single point of data taking, we have 2,500 bunches, where each bunch has a few trillions of protons. At their end velocity, they rotate roughly at 11,000 times per second. And the gap between the bunches is 7.5 meters, which corresponds to 25 nanoseconds at their end velocity. They're always spaced by this distance, except for one part of this beam, which is kind of the escape route. So if we need to dump the beam, we actually have a gap where we can really, really fast stare the beam out and slam it into a 3-meter block of graphite and get rid of it so it doesn't burn through the ring. So when these bunches hit each other here, or they meet each other in the center of one of the detectors, I'll use CMS as an example, which is where I work. We have these bunches coming in, we bend them, we squeeze them tighter together, and we hope that some of them will hit each other, because most of this is air. So out of the trillion here and trillion here, roughly 60 pairs will collide at every bunch crossing. So the probability of collision is extremely, extremely low. When they collide, the energy of the incoming protons gets converted into the mass of new outgoing particles. So the protons are gone and they create new particles that shower through the detector in all directions. And we have coverage all around the interaction point. Ideally, this thing would just be a sphere, so we could look everywhere, but a cylinder is a good approximation of a sphere because we need to access things. What do we study? Well, we have our fundamental particles that we'd like to study. When you take pictures with your camera, you only need to be sensitive to this one thing. So the camera can be pretty small. It only needs to detect this one type of particle. We need to detect all of these, and they're extremely different. So for instance, just their masses span orders of magnitude. So that means when we build our detectors, we can't just have a camera sensitive to this. We need a camera sensitive to all of the different types of particles, which means we design them in a layered way. So here you can see our detector from the front. So here one proton beam goes into the screen, another proton beam comes out, and they collide here in the center. And we have layers of detection material that does different things. So here you can see kind of a slice of this detector. Now, what will happen is if you have a particle like a muon, we design the particle in such a way that the muon leaves a specific trace. And we know that if it's a muon, it will leave some signatures in the inner tracker. And then it will go as the only particle, it will go all the way through the detector and out. So we will detect it here. It's also curved because we have a magnetic field that bends charged particles, and we can estimate their energy from the curvature. Then, for instance, if you have something like a quark, it will hadronize and produce a spray of particles that we will detect in the hadron calorimeter. So all of these layers are there to detect different types of particles. So when we do something like discovering the Higgs boson, the Higgs lives for 10 to the minus 28 seconds, so it's instantly gone. And it decays into 2 new particles that then again decay into 2 new particles. So we look for collisions that are compatible with these 4 particles. That's a sign of the decay of the Higgs boson. And it's extremely improbable that we produce a Higgs boson. So we actually had to collide trillions and trillions of protons, and only 10 of these collisions were compatible with the Higgs. And we could announce the discovery of the Higgs with those 10 events. The problem with all of this is that every single collision is a few megabytes of data. And I told you already we have 1 billion collisions per second. That means a petabyte of data every single second. That's the whole Netflix library every single second in a radiation shielded cavern 100 meters underground. Now, if we could read out all that data, and that's usually the first question, yeah, but you have big compute center, why can't you read out that data? The problem is that I told you the thing about a sphere versus a cylinder, that we want to see all the angles of the collision points. If we want to read out a lot of data, we need to put a lot of cables in and readout chips. And as soon as we put cables in, the particle isn't going to go through any detection material. It's going to hit the cable or the chip. So that means if I want to read out more data, I make my detector worse, because suddenly the particle is not hitting particle detection material anymore, it's hitting a cable. So there's always this trade-off between how good is your detector versus how much material is in your detector. So if I try to read out all of it, great, I would have a crappy detector. So instead, we do this very funky trade-off where we say, okay, from quantum field theory and the standard model of particle physics, I know that the probability of producing anything at a center of mass energy of 13 TeV, which is where we're running the LHC, the probability of producing something interesting like a Higgs is all the way down here. So even if I could keep all of the collisions, I'm actually just maybe interested in this down here. I should be able to do some filtering out of the stuff I'm not interested in, do it within a short amount of time. So we rely on that. And then we go back to our detector as a petabyte of data per second and collisions every 25 nanoseconds. Here's the detector again. Here's the beam pipe. Collisions happen here and the particles spray through the detector. Roughly a few megabytes of data. What we do is that one collision happens. All of the information from this collision, I buffer inside the detector on buffers, on ASICs, basically. So I have a buffer that can keep the collision for a certain amount of time, depending on how big it is, and then the collision falls off the cliff. And that buffering time is a few microseconds, 10 microseconds. Within that time, I can keep that information inside my detector for that time. Within that time, I say, okay, I cannot read out a few megabytes of data every 25 nanoseconds, but I can read out 1/5 of a megabyte of data every 25 nanoseconds. So I take 1/5 of that information, I buffer all the information here. I take a reduced set of information that I need to choose myself, and I send this to a computing farm, basically. So this is now still 63 terabits per second of data. It's 5% of the total internet traffic per second, basically. So there's a lot of data still. A subset of that data is sent to this processing farm, which now has the buffering length of time to make a decision whether or not to keep this event or not. So here we go from a bunch of voltages and sensors to trying to reconstruct particles that shower through the detector and say, keep this collision or not. So here we have 1,000 or so of what's called field programmable gate arrays. I'll talk about it later. It's specialized hardware that has this job of getting rid of 98% of the collisions within 10 microseconds. So within those 10 microseconds, this whole processing farm needs to send a signal back to the detector. It's either 0, reject, which means that collision will fall off the cliff of that buffer and no one will see it again, or it is 1, keep. So it sends that signal back to the detector, 0 or 1. 0, it's gone forever. 1, and only if it's 1, does that data leave the detector. So up until this point, no data has ever left the detector itself. It was only inside those buffers. So now we've rejected most of the events, and we have 200-meter fibers, almost 600 200-meter fibers, that has the job of taking that reduced set of data and sending it to the surface. So now I got the data out of my detector. I have no time constraint anymore. Those 10 microseconds were only because I had to keep that event until it falls off the cliff. Now I have infinite time. Why am I still not keeping all of that data? It is because in order to go from the tiny voltages in the sensors and reconstruct it into particles going through the detector, I need to run a lot of computing code that takes 20 seconds per event. If I would run that on all that data, it'd be done in 3,000 years. So I actually cannot still reconstruct and store every single collision I have. So I have to get rid of even more. Now I have more time. I have hundreds of milliseconds to, again, now look at the full 100% of the information and make a finer grained decision on the surface. And I do that on 30,000 CPUs, 400 GPUs, and I have 300 to 500 milliseconds. And I reject now so many events out of the 100%. So you're left with extremely little that you now have to be very careful in selecting, because I showed you this measurement that we're now doing in 2025, which is measuring this mass of the W particle to the sub per mil. And that's not the only thing I have to measure. I have to measure all of these parameters of the standard model in particle physics to 5 sigma level, which means when I select that data, I need to be extremely careful with what data I select. So to make sure we get the right 0.00025% of the data, which is what we do to make plots like this, algorithms needs to be very fast to get more data through the system and very accurate to select the right data so I can measure the W mass to a precision of blah per mil or discover the Higgs boson. Now, we've already discovered the Higgs boson. So why am I saying all of this? Well, it's because there are other things we're interested in. We know the Standard Model is an effective theory that breaks down at very high energies. So I know it's Newton's theory to Einstein's GR, basically. And in order to look for that new theory, I look for new physics, with probability of production is extremely low. So if I have to collide trillions of proton events to discover the Higgs, I need to collide billions of events to discover some new physics. So within the next 5 years at CERN, our main job is to upgrade to what's called the high luminosity LHC. End of next year, we'll end the LHC, and we will start building this new detector and accelerator, where basically what we do is 2 things. It's double the amounts of protons per bunch and squeeze them tighter together, which means stronger magnets to make sure the probability that they overlap is higher than producing 60 pairs colliding every crossing. We want that to be a factor of 10 more. Great, we'll have a factor of 10 more data. The problem is, if you go from this average of 60 protons colliding, if you look at the size of my pinky finger, 6 centimeters, every yellow dot is a pair of protons colliding. When I run my physics analysis, I need to disentangle which one of these particles came from which of the yellow dots and what were their energies and which hits belongs to which green dot and yada, yada, yada. And imagine doing that in this environment. It's still 6 centimeters. And now you have up to 200 of these simultaneous collisions. More data, more probability of producing something interesting, but a huge mess. So in order to be able to deal with this extremely high complexity data extremely fast, we're looking at using AI inside the detector itself, where we have those little ASICs that needs to do the buffering of the data and choose which data we send out to the level 1 trigger or to the surface. and in this level 1 trigger system. So this might sound like a novel and great idea, but actually the second paper in particle physics proposed to do exactly that in 1987. So this is something that we have been thinking about for a long time, and which is only now becoming feasible because of new techniques that have been developed that allows us to do this very, very well. So first I wanted to show you quickly what such a system looks like, such a trigger system. So here it looks kind of abstract, and here you can see what it looks like in real life. We basically have a bunch of board equipped with field programmable gate arrays, chips that you can reprogram, like ASICs that you can reprogram to do whatever you want. They process, you've seen this picture before, these 1,000 FPGAs. We have some of them responsible for doing some low-level calorimetry reconstruction, some that are responsible for the charge track reconstruction, some that are responsible for the muons, and some FPGAs that combine all of that information. And here we make a decision, like 124 ORs of, is muon energy above this, or is jet energy above this, or is electron energy above this, then keep or reject. So the total time is 12 microseconds for this upgrade. But as you can see, this is a really staged system. So this part needs to be done by 5 microseconds. Some of the algorithms here needs to be done in 50 nanoseconds. So that means it's extremely, extremely latency constrained. And if you go and talk to industry, I mean, your smartphone on your smart headphones, they don't need to do AI in 50 nanoseconds. A few milliseconds is enough for you to have a good user experience. So that means we have had to develop new techniques in order to be able to process this data within 12 microseconds in total, processing 5% of the internet traffic. So ideally, we would love to have GPT do its magic stuff inside the system, but in reality, we have our tiny chips that needs to do inference in a few microseconds or nanoseconds. So the first thing we did is figure out how can we put machine learning on this thing that's called field programmable gate arrays. So here you have a machine learning algorithm that basically does what AlexNet did in that revolution of AI in 2012. It looks at handwritten digits and it tries to classify it. Shawnee actually made this, both of these. So an FPGA consists of a bunch of different resources that you can program to talk to each other. So if you want to do A plus B equals C, you can program this chip to do A plus B equals C. And then you have an ASIC, basically. This was usually used for prototyping ASICs, and now we use it for many more things. Now, to put machine learning onto these chips, it takes a lot of experience in writing hardware. So instead, we worked on making a library that can automate everything that takes you from nice Python code that students know how to work with and physicists know how to work with, translate it into something that you can put on hardware. What's cool about why aren't we using CPUs or GPUs? What's cool about FPGAs is that we can program them in a data flow architecture type of way. What does that mean? It's very different from a Van Neumann type computer, where a Van Neumann type computer is basically inherently sequential. It does sequential operations. In a data flow architecture, it's all based on availability of data. As soon as data is available, it launches the next step. So you can make it extremely parallel. And a CPU, you can run any piece of code on it. For us, we really make the hardware for a given model. So we take that model and we turn it into a hardware block because it's the most efficient thing you can do. So that means anything you decide on in your model, you have to do it before you put it on this FPGA. It will only be able to run your model. Each layer is also a completely separate compute unit, so you can tune it exactly as you want. Now, one of the problems that we have with this is that the latency is so low. So we need to reach this 50 nanoseconds latencies that I told you about before. And if you want to have a big model, this tiny FPGA is already completely full. If I want to put a big model onto this thing, what I could do is put external memory there to keep some of it. But the time to send the data to external memory and back is already killing you. You're already far above your latency constraint. So everything needs to happen on the chip itself. So that means, hey, you actually cannot just take whatever model. We made this great library, it just translates everything automatically, but that everything is a small subset. You have to do a lot of massaging here first. So we had to attack that first. So the first thing we did is say, okay, floating point computation, a way of representing numbers so they can be very granular around 0 and also have a very wide range from 10 to the 38 to minus 10 to the 38. You can represent huge numbers and very small numbers. It's very great, but they take a lot of resources on hardware and they take a lot of time to do multiplications between floating point numbers, additions. So we said, okay, no, let's reduce the amount of information and use integers instead. And fixed point representation is a convenient way of representing fractions as integers. Think of it as integers, where instead of having all of these different values, you now have to put your numbers into buckets. So if you have 4 bits, you have 2 to the 4 buckets, you have 16 buckets. So the weights of your neural network can only go into one of these buckets. If you use this type of representation, you use way less resources on the chip, and it's way faster. So we really think, okay, how can we manage to make neural network weights in these buckets, basically? So what we did first is like, okay, let's take the neural network and put those numbers into buckets. Then what we saw is that the accuracy of our network, as we put them into fewer and fewer buckets, went down and down and down and down and down and down until you had a coin toss at 50%, because it's lossy compression. Instead, we thought, okay, we have to do this in a smarter way. Let's let the network know that it is being quantized, it is being put into buckets. So when we train the network itself, we say, hey, when you go onto a chip, you will be inside a bucket. You won't be able to be anywhere. You will be inside a bucket. Optimize yourself to be in the right bucket. So we tell the network at training time exactly which bucket it needs to go in. And in that way, you can have exactly the same accuracy for a model that now has weights that go into discrete buckets of maybe as small as 16 buckets. And make this very, very easy to work with, where you can run everything in Python and you can define each of the layers of your network to be whatever, how many buckets you want, basically. Secondly, we said, okay, you have a neural network where you have a bunch of different neurons inside that does some work. Not all of the neurons does equally much work. Some of the neurons are really important to the network. Some of the neurons don't carry much weight. So let's remove those neurons that don't do a lot of weight. Let's cut them away. Cut these ones, this one away, that one away. Now we can remove up to 50% of those computations. So here you can see the same network, the network weights before some of the weights were cut away and after. And all of this spike at 0 will just be removed on hardware. So then you can make the network even smaller. The second approach we used was to say, okay, look into literature. What are people doing that have to serve these very big LLMs and do it really, really fast? Which is knowledge distillation. So can you have the best of both worlds? At training time, you can train your beautiful big network. And then when you put it on your chip, it can fit on this little tiny thing. And knowledge distillation works the following way. Let's say you have a huge neural network that can classify cats from dogs. It's big, it's great, and it can do this really, really well. Whenever it gets some data in, it can rightly classify the probability of this being a cat versus the probability of this being a dog. So it's already trained. Now you say, okay, this is my teacher. It knows everything about cats and dogs, and I've already trained it. Now I take a completely new data set in that I pass through the teacher, and it gives me a probability of this being a cat and a probability of this being a dog. Then I take another network that now has a size that fits the device I want to target. This is way smaller. My data set has a true label, is cat or is dog, but it also has a soft label from the teacher. That's a probability of this being a cat and a dog. Now, why is this important? It's important because if you as a human look at this picture, the true label is that this is a dog. But if you look at this picture and tell me honestly, what animal is this? And the teacher knows that, right? Like he's 50% sure. Whereas the true label doesn't carry much information. And this, I mean, this is a beautiful dog. And the teacher thinks so too. So if the little student can get the information from the teacher that's like, oh yeah, maybe a cat, maybe a dog, it's learned subtle knowledge. and the true labels, you can distill the knowledge from this network into the teacher by training it to predict the labels that are true and training it to predict the labels of the teacher. And this is actually used, if any of you use Gemini from Google, it's actually used in Gemini, where they go really, most of the prompts you do in Gemini go through a smaller model that they obtain from the big model via knowledge distillation. So it will first pass you through that little model, and if you're not happy, they pass you through the big model. So they use this in production, and we use it in production in our triggers because some networks are far too big to fit the chip. Okay, 2 examples where we are using this in the trigger. For compression, I told you we have a few megabytes of data here, but I'm sending out 1/5 of the information. You're like, oh, wow, Thea, how did you do that? Like, how did you reduce that amount of information inside your detector? So in 5 years, when we are building this new high luminosity LHC, we're upgrading our detectors. And here again, you have CMS, and this is the very front part of the detector. And the probability of producing particles that are very forward are way higher than the probability of producing particles here. So there's a high density of particles in this forward region, which means it's blasted by radiation all the time. So it's completely dead. So we have to replace it, and we're buying a new one. That's called the high granularity calorimeter. It does a really beautiful measurement. It has layers, fine granularity. We never had such a great calorimeter before, but it has 6.5 million readout channels, which is too big for us to actually read it out. So we have fantastic information in the detector, but cannot get it out. So what we do is we have all of the information in these dots. These are the sensors of the detector, and it has some chips glued onto it. And some of them have the job of compressing that data and sending them to the level 1 trigger. So you have to do that on the detector where you're bombarded by radiation. The whole thing is cooled to minus 30 degrees, and also you don't have a lot of cables, so extremely low power, everything that runs there, and you have to be really, really fast. So what we've done is that we've taken that cell and we've trained a neural network, a little AI, to compress that data and decompress it again. That's all it's trained to do. Optimize these weights to compress and decompress, compress and decompress, compress and decompress, until it's trained for ages. And most of the information of the collision is now in this bottleneck because it's able to say, if I have a lot of information here, I need to compress it to something small and then decompress it again. I should only store the most important information. It's like a principal component analysis, basically. Take what kind of gives you the biggest variance in your data. So now you have the original information stored in this tiny bottleneck. What we do then is that we take that encoder and we glue it onto this ASIC, and we put it inside the detector. And now this bottleneck is what's being transferred to the level 1 trigger, where we then can decode it again and have the original cell information. So these things are really, really small, like sub-watt, 75 to 100 milliwatts. All of the weights and biases of the neural networks are triplicated, because if there's radiation, you can have a bit flip. So then it's a majority vote. If one of the bits flip, you do a majority of the others, and then you say, okay, this was the real number. And the weights are reprogrammable. Finally, one example on what we use it for here. So here in this system, we're exploring machine learning for a lot of different things. I'll talk about the one I'm most excited about. So I told you that we filter these events in the level 1 trigger, and the example I said was, is jet energy above 300 this? Or is muon energy above this? Or no. And that's how I choose the events. But that, of course, means that if I have asked, is jet energy above 300, and I keep only this, new physics can, of course, be down here. Who says that new physics doesn't have low energy, for instance? So is there a smarter way for us to select these events? And the idea is, yes, we can actually train a neural network to recognize how normal data is from the data itself. Look at all of the collisions, learn the probability density of that data, what's normal, what's not normal, using modern machine learning techniques, and select only what is abnormal. So how does that usually work? So this is kind of inspired by financial fraud detection. I don't know if you have that too. Sometimes when I use my card in a weird place, it's like, oh, now you have to type your code. And usually that's some sort of anomaly detection. It's trained to recognize your normal behavior And then it looks for outliers, basically. So the same in this way. So it's you train again an autoencoder to go from the original input to a smaller dimensional embedded space up to the original again. And it will learn this really, really well, but it is reducing the information content. So as soon as data comes in that's very different from what they trained on, it won't be able to reconstruct it very well because it hasn't really been focusing on those outliers. It's been focusing on getting the bulk of the distribution right, not the weird tails. So what comes out is very different from what comes in. So just the mean squared error or the difference between out and in is some sort of degree of abnormality. And then you can say, okay, what was my error on reconstructing this? If I had a large error, I keep it. And I've learned what's normal directly from the data. If it's normal, I reject it. So there you have a completely unbiased way of selecting what you want to keep based on the data itself. And this is something we're doing in 50 nanoseconds. It's taking 300 events per second at the CMS right now. And this is the very first time we're actually using AI to select events in such a system. Finally, also outside of particle physics, we've been working with Volvo on semantic segmentation for self-driving cars, a group working on ASIC implants in your brain to do epilepsy seizure prediction, so give you an alert that an attack is upcoming. Shawnee works on Earth monitoring in satellites, looking for plastic waste in the ocean, all with these type of fast machine learning techniques and many, many, many more. And I think this is really kind of the future of big science. It's a data problem. I don't know if it's the same in information in your world as well. We know in the future we'll have a petabyte per second of proton collision, but we also know for big telescopes that takes pictures of the night sky, they will have huge data rates in the future, and they don't really know how to handle it yet, and are looking into ways of doing that fast with AI. Same for big Cherenkov telescopes that looks for charged particles from outer space. They also will have vast amount of data and are now deploying more and more AI at the edge in order to process that data. So I think this is really where we will really see AI making the biggest difference in scientific experiments. And that's all I have. Thank you very much.
Thank you very much, Thea. This was a really inspiring, upbeat talk, I think, It's very complex matters you are describing, but you make me feel that I have understood it all. The problem is when I get home this evening and I try to reproduce all these explanations, I'm not sure I will be.
YouTube.
Exactly. I'm not totally sure I will be able, but it's, as I said, inspiring. And librarians who have to deal with all the corpus of information in this world, if you want, should really be inspired to see that it is possible to handle this enormous amount of data, because the data we have to deal with is probably still much less than what you have to deal with. And we have at least more time when you get to deal with it.
Maybe we can use our equipment for the replacement of physicists.
I am sure we can, So I think we should open up for questions. And do you follow in the Zoom, maybe Salome or Sarah? So far, no questions there. Any questions here in the audience? Martin?
Yes, thank you very much. Very interesting part. I have maybe a little provocative question. In the end, you were talking about some like spin-offs where it could also be used. But when I think about it's a radiation-hardened, extremely fast, automated decision-making system called Trigger.
Yeah.
There is one use which immediately comes to mind, which is military use.
Yeah.
And so the CERN convention basically rules out any military use. But in the same time, you also say CERN research has to be open, and we are famous for being very open. How is that addressed?
It's funny that you're saying this because we just had a discussion the other day about changing our license for these softwares to a license that's like use for good only. So it's still open source, but has kind of a use for good clausule in them. So there exists solutions to trying to address these at least. So that I think that's the only way you can do. We want to be open source. Then if it is open source, it is open source, but you do at least have some way of protecting yourself through licensing. That's as far as you get, I think. It's like the hammer, again, can be used for good and evil. Yeah. But personally, we do try to avoid any collaborations that involves huge financial gain for some or military gain for others.
I imagine a lot of pressure, especially in time, that there is some interest to use that, I guess.
I think there's a lot of AI in military research, but I'm not involved in any of this dialogue at all. But I know there's a lot of kind of smart inference in camera, a lot of body shock, real-time detection in this, yeah, a lot of use cases.
Thank you very much. A question to the audience. This intervention came from the room. Could you hear it well out there? It was okay. Okay, we have someone with an earplug here in the room which said it was okay. There are two questions in the chat. I don't know if you would like to come in and ask your question in voice, or if I should just read it out. Then I read out. It's a question from M. Stout. Thank you for the great talk. If sample preparation changes, how often do you have to retrain your large language models?
We don't use language models, we use similar architectures, but how often we have to retrain is something we study actively, because detector conditions change frequently. If there's a little, every time during a fill, when we fill the storage ring with protons and start taking data, the sensors themselves even change during minutes, hours, sessions. We have changes at the very small time scales and changes at the large time scales. So we're studying how often you have to do that. This is something we don't know yet. But it really depends on which part of the detector you're working on. I mentioned this part, that some parts of the detector have more radiation than others, and they're then very vulnerable to changes from just being blasted by particles, and some are less vulnerable. So this is just an active study. And there are mitigation techniques from industry as well as within our field on how to overcome that by slowly, by retraining or gradually adjusting.
Thank you. This was my
I
question.
see that you
Sorry,
turned on
couldn't
your
ask
camera.
it
Would you like to
before.
come in?
Yeah, no, it was my question. I just wanted to say thank you for
don't
answering
hear
it.
you. Let us not see.
Maybe you unmute.
Please come now. Come now. No. Let me see. How do we do this?
You can go out.
But then you won't hear it. Come with me. Let's just read.
Yeah,
we want to say something. We will manage.
I won't hear anything, right?
Can you hear me?
Oh.
I know it's okay. I just wanted to. It's okay. I just wanted to say thank you for answering my question. The first one was my question. Thanks for the nice talk.
Sorry that our web setup was not so perfect technically, but we have also a question from Albert. From the presentation, it's that you are working on interference at the edge. Are you also working on training, fine-tuning of models on FGPAS on the edge?
Some people are looking into it, but so far nothing we have deployed is being fine-tuned or trained at the edge. But it is also an area of research if you can do small adjustments, at least on the device itself. So definitely an interesting thing to study.
Wonderful. Are there other questions, comments? Sorry that had not practiced on the interaction. If there are no questions, I think that I would thank you all for having participated. Everyone stayed for the talk. I can tell you that was not that was already good. And for those of you who are in Zurich, please note that Thea is based in Zurich, you know, so and she is always very accessible, I have to say. So I think don't hesitate to contact her. And thank you very much for having taken part in this session. And if you are still not exhausted, in half an hour, the Innovation in Scholarly Communication workshop will start online as well. So hope to see you back. Bye-bye, everyone.
Bye-bye. Bye-bye.